on Sunday night though, all right? Because that we will definitely spend most of Monday working on. Okay, again, you guys always have the advantage of me like having done this twice already this morning and deciding where I want to go with it. Okay, let's do this. I think I drew this molecule once already, but I didn't have you guys draw it. So I want you, and I'm going to use this space because we're going to have to actually look at the bottom half of these rules in a second. So I want you guys to draw carbon monoxide for me. Okay, carbon monoxide is a real molecule. And I want you to do the normal thing where we put the valence electrons on and connect the dots and blah, blah, blah. I'm also going to throw this out there right now because there is some question about like, well, this usually happens and this usually happens and this usually happens, but what's firm? So I'm going to tell you the things that are firm that have to come at the highest priority of your list when you're drawing these structures. Carbon, nitrogen, oxygen, and fluorine will always follow the octet rule. Those are the only ones that it's actually a rule for. Today we're going to look at the fact that boron and aluminum, which are metalloids, and even beryllium, which is a metal, can actually form covalent bonds sometimes. And they very often, if not always, will not fulfill the octet. So I say they underfill, meaning they have less than 8 electrons surrounding them. And then anything beyond the second row, so we'll say row 3 and on, can, it doesn't have to, but can overfill, meaning can have 8 plus electrons. Okay, so keep those in mind as we're working through stuff today, but go ahead and start on carbon monoxide. So carbon monoxide, you C and O, they have to fulfill the octet rule. Okay, so this is what you should have started with, and you should be a little bit confused. Because carbon looks like it wants 4 bonds, and oxygen looks like it wants 2, which is what we always expect. But there's no way to bond 2 things together with 4 and 2 bonds, okay? So let's start with the 2, because we know that's at least going to happen. And then let's see what we need to do. The only option here is to take an electron from oxygen, give it to carbon. Okay, so I'm going to cross it off the oxygen and give it to the carbon, and then form that 3rd bond. So nobody's perfectly happy. hate saying happy. I try to avoid that as much as possible. Nobody is going to be perfectly fulfilling the number of bonds they usually form, but there's a little give and take. Oxygen forms more bonds than it usually wants. Carbon forms less bonds than it usually wants. But the way that that happened is by oxygen giving the electron to carbon. All right, there is an accounting system called formal charge that we use to keep track when we move electrons away from the atom that brought them into the molecule. So formal charge is not an actual charge. It's not like if oxygen gave its electrons to calcium, okay? In a metal, non-metal situation, that's actually what happens. Calcium, other way around. Calcium gives its electrons to oxygen. That is not what's going on here. They are sharing it in a weird way, but for the purposes of keeping track of the fact that the sharing is weird, we're going to use charges in the same way that we used them for ionic bonds. So it looks like we had to move an electron to oxygen. So when we remove an electron from something, we say it has a positive charge, right? Like if sodium lost an electron, we give it a positive charge. It now has less negative. So we're gonna say that oxygen has a formal charge of +1 because we moved that oxygen away from it and we gave it to carbon. So we say that carbon has a -1 formal charge. All right, there is let's pretend that I just gave you the molecule, the Lewis structure, thank you. Let's just say I gave you this Lewis structure. I didn't have you draw it. I just said, this is the Lewis structure for carbon monoxide. Assign the formal charges. You might not recognize immediately that I'd had to move an electron from oxygen because you weren't the one drawing it. So let's go through a process that can help you determine what the formal charge is, even if you weren't the one that drew the molecule, okay? So this is put in great detail right here. So I'm going to explain in nice, tidy method words what this says. So if you need to come back to this, that's fine. But don't start there because it might just feel confusing to have too many words, okay? All right, bonds are made up of 2 electrons, right? I'm gonna draw those electrons in on the lines just to remind us that the line means 2 electrons. And then I'm gonna divvy them back out to the 2 atoms that they're connected to. And I'm gonna compare how many valence electrons did this particular atom, let's use oxygen, how many valence electrons did oxygen start with when it was just an atom, when I put down its Lewis symbol? And how many electrons are surrounding it now? Not counting, like when we do the octet rule, we count all the electrons, we count the bonds twice. We're not counting the bonds twice here. We're divvying out the bonds. And we're saying just the ones that are immediately around the oxygen, how many are there? Okay? So when I look at that, I see that there's 5 electrons right around that oxygen, but there used to be 6. And that is another way I can figure out that an electron got moved away from the oxygen. Because normally, like in CO2, when we, let me actually, before the bonds are there. In CO2, I know I drew those at kind of weird angles, but It started like this, and we made the bonds, and nobody moved anything anywhere, okay? It just got bonded with the oxygens, and all the electrons stayed right where they were. So if they stay right where they are, then it's a zero formal charge. We'll do that on CO2 in a second, but let's just hone in on carbon and oxygen in this one for now. Okay, other side, carbon. It started as 4, it now has 5, so that's why its formal charge is -1. It gained that electron. And this method allows you to do that without being the one that moved the electron over from the oxygen and showed that it moved. Okay, you're just using the fact that you know it started as 4 and now you see 5 surrounding it. So it gained an electron. Or you know it started as 6, but now you see 5 surrounding it. So it lost an electron. Going back to carbon dioxide. So let's do the same thing for carbon dioxide, knowing that when we drew the structure, we didn't move any electrons. We just left them on the atoms that they started with. Okay, I'm drawing out those dots that are part of the bond. I'm going to look at just the electrons that immediately are surrounding the atom. Well, of course they match what they started with because we didn't move any of them, right? We didn't move any electrons from carbon, so it started with 4 and it still has 4. So that's a 0 formal charge. Oxygen started with 6, ended with 6. So 0 formal charge. And we know that that's the case because when we drew the structure, we didn't have to move anything. We just paired things up and everything worked out nicely. Okay, why does this matter? Sometimes you are going to have structures where there are multiple options of how to draw it, and you are going to have to use formal charge to determine what the best structure is. I'm going to wait and save it until after we talk about over and under filling to show you an example of this, of how we pick the best structure, because the best example of this is one that happens to overfill. So we need to explain that first before I can show you that as an example. Okay? All right, underfilling and overfilling. So this is the notes we did yesterday, last class, I mean. We didn't get to this one, and I decided that you guys, the new method that I've been using for Lewis structures totally negates that anyone would do that wrong. So skipping over that. Okay, let's start with SF4. I'm going to do this one with you guys, and then I'm going to have you do SF6 by yourself. Okay, so I said sulfur. Well, I need a periodic table. It's annoying because my there's got to be a remove all apps, right? Okay. My other classroom has a periodic table in it, which is much nicer. I'll just switch back and forth though. Okay. Everything in this row, we said, or I just barely said, is going to have the ability to overfill. So this row and beyond. All right. Now, technically, we're really just talking about the nonmetals over here, because those are the ones that are forming covalent bonds. But for your memory, think of it as the third row and further down. Why is this? If we look at the orbitals of sulfur versus, say, oxygen, this is what oxygen looks like. And then it goes up to the third energy level and so forth. Sulfur, the bonding on sulfur, its valence shell, is occurring in n equals 3. Well, guess what? There's not just s and p orbitals in n equals 3. There's also d orbitals. But they haven't been filled yet. They're just there at that valence shell. So you get to use those to bond sometimes. If you took chemistry in high school and maybe just 1 year of it, you probably got it drilled into you that everything needs to have 8 and it can only have 8. Okay? So this bothers people sometimes that we are going to put more than 8 electrons around an atom. But it's okay because now you have an advanced understanding of where the electrons are. And if you're in that third energy level, you now remember that there are d orbitals there. And that's all we really need in order to be able to put more electrons is more orbitals at that valence shell. Okay? So the example we're going to do right now with sulfur, it works for sulfur. It would not work for oxygen, though, because oxygen does not have those additional d orbitals in its valence shell because it's only at n equals 2. Okay? So I'm going to start my normal way with drawing out the Lewis dot symbols. And the first couple should be fine. And then I'm like, wait a second. The sulfur doesn't look like it wants to bond anymore. It looks like it's all good to go, but she's telling me that there is a molecule called SF4. So I have to figure out, how do those bonds form? Okay, those other electrons that are in a pair, they're going to split up and they're going to form bonds with the fluorine. The only time that really happens is the only time. Probably the only time. I can't think of an example off the top of my head. Probably the only time that this happens where you take a pair and like separate it and form bonds with it is when you're overfilling something, when you're going beyond those 8 electrons. Where is, this is a highlighter, right? Oh, nope, that's the eraser. Okay. Looking at the number of groups that are surrounding the sulfur, so this is not formal charge, that's not what I'm doing right now. I'm just looking at, is the octet satisfied? It's more than satisfied, right? It has 10 electrons surrounding it, 5 groups. It doesn't have to. Sulfur will sometimes just have those 8, but it has the capability to now. There is no OF4 molecule. This could not happen with oxygen. Okay, so go ahead and do this for SF6. looks weird. Someone asked me in my other class, like, I keep drawing the dots in the wrong place. And I'm like, there's no right place. Just clean up your structure when you're done. That's all you need to do. Oh, that wasn't very clean. You can't really use copy and paste, I'm realizing, if you're gonna clean up your structure. Okay, so it really is that straightforward. You're just allowed to break up those pairs now and form new bonds with them. Not required, again, but allowed. Okay. Yeah, let's just look at formal charge on this. Most of the times, things that have zero formal charge are things that have the predicted bonding. So we said carbon wants to always have 4 bonds. That will give it a formal charge of 0. Nitrogen wants to have 3 bonds and 1 lone pair. That will give it a formal charge of 0. So if you're looking at a structure and you see it has like the expected bonding, like fluorine has the expected bonding. It has 1 bond, 3 lone pairs. So without even doing any calculations, you can verify it, but without even doing any calculations, I know that the fluorine all have 0 formal charge because they have 3 lone pairs and 1 bond, and that's what we expect to see. Just because it doesn't have the expected, though, doesn't mean that it has a 0 or doesn't have a 0. That was like a lot of doesn't and isn't. Sulfur does not have the expected bonding. Let's check its formal charge. Okay? So I'm going to divvy out those electrons. You don't have to draw the dots every time, but if it helps you, great. Okay? Sulfur started with 6. It still has 6. So it is also a 0 formal charge, even though it doesn't have the expected bonding. So if it fits the bonding you expect, you know it's 0. If it doesn't fit the bonding you expect, check it. It might be 0, it might not be. All right, underfilling. I've already told you, let's look at it on the periodic table so you see where they are. Different color and highlights. Beryllium, boron, aluminum. Those guys will always underfill. It's not even just that they can, it's that if they're gonna form a covalent bond, they will underfill. So we're going to look at 2 examples. I'll do the first one with you, and then you guys can do the next one. Same approach we've always done. Draw the Lewis dots, remembering that beryllium's in the second column, so it has 2 valence electrons. The fact that they're not paired, because we haven't gone around the 4 sides yet, is a good indicator that it wants to form 2 bonds if it's covalently bonding. It is bizarre that it covalent bonds. Let's see. I'll look at what the numbers are. Don't look, because if it's not this case, I don't want you to get confused. Yeah, it's not. Don't look. Just know that if I give you a structure and say draw the Lewis dot symbol for this covalently bonded molecule, trust me that it happens. Okay, as long as you can be okay with that, it's all good. The reason you need to be okay with it is because beryllium, boron, and aluminum will underfill. The other option, if you weren't okay with it, so we're going to show you what you might have done and why it's not good. This is kind of similar to CO2. Okay, you draw the bonds, and then you're like, well, beryllium's octet isn't satisfied. It only has 4 electrons surrounding it. So what I'm going to do is I'm going to give an electron from fluorine, from each fluorine actually. I'm going to give those to beryllium. This is not really what happens, but I want to play devil's advocate for a minute. Okay, and if I do that, then I can form enough bonds that the beryllium and the fluorine have their octet satisfied. And in the case of carbon monoxide, I did do something kind of similar to this. But I'm telling you, this will not happen with beryllium, boron, and aluminum. It will happen with carbon, oxygen, nitrogen, and fluorine. If those are the only atoms. Obviously, fluorine's in here. But because there's beryllium in there, underfilling is going to happen for that beryllium. Okay. In order to prove to you why this is a bad idea, I want you to assign formal charges. So on your own, or with your neighbor or whatever, but not with me, go ahead and assign formal charges for the 2 fluorines and the beryllium. Mm-hmm. Yes, the equation should work out fine. Yeah. If you're not totally getting how to do that, chat with your neighbors. Nobody is ever convinced of this, but like it's always beneficial to both of you. The person who's confused understands it a little better. The person who understood it understands it even better because they've explained it. So Maggie asked me, can we use the equation that's like in the book and that's in the notes? Yes. So that says valence electrons in the unbound atom, meaning like fluorine comes in with 7, minus the number of electrons that it has in the structure. So that's 6. So this is how we figure out that that's a -1. So you're just comparing what did it start as, what does it have now? Is it the other way around? No, it is +1. You're just right. The formula is right, just the math. You'd never know that I already had 400 milligrams of caffeine this morning. It's like 2 coffees. Don't freak out. Okay. Beryllium came in with 2. Now it has 4. That's actually -2. And this should make sense because when we drew the structure, we gave an electron from fluorine to beryllium. So fluorine lost an electron, beryllium gained 1 from each fluorine, okay? You could calculate that, though, without knowing that that's how we drew the structure, right? Okay, why did I want to do this? Because now we're going to talk about formal charge and how it can help us know if a structure is good or not. Yeah?
The correct way to draw it is the first one.
Yes, yeah. And let's just really quickly, let's look at the formal charge of those. So 7, still 7. So this one's 0. Same thing over here. Beryllium, 2, still 2. That one's 0. So the way that I'm going to defend that it's the correct one is with the formal charge. So when I look at the formal charges, there are a couple things I'm looking for. And this is articulated in those notes where we had the first 5 rules that I just basically threw out the window. And I said, let's use this other method. And then underneath that are the rules for finding formal charge and then what we're going to prioritize. Okay? The things we are going to prioritize is that we want the numbers to be 0 if at all possible. Okay, so off the bat, that means that this structure is better. We didn't break any of those rules about who has to have the octet and who underfills and who overfills, and everything was 0. There will be instances where it can't necessarily stay 0. In that case, it is preferable to be close to 0. So if I had an SO and these guys were both 0, obviously that's best. If I have the example I used was with 2 oxygens because that's what we're headed to right now with sulfate. If I had -1 and +1, that's kind of my second best option. This isn't really going to make sense, but I'm going to do it. Versus if I had -2 and 0. Yes, there's a 0, but it's always better to have multiple 1s than to have, oh, that's what it was. I want this guy to be -1 and -1. Okay, so this is our best option. This is our middle ground, and this is terrible. Okay? I want to keep the numbers as small as possible. Even if it gives me a 0, don't give me a 2. Do a 1 and a 1. Separate that charge out. These are representing electrons. Electrons do not want to be squished together. They're all negatively charged. So a -2, you're basically saying I'm squishing 2 extra electrons on this atom rather than 1 or just not any at all. And then the final rule is if you have to have charge, formal charge, put the negative on the more electronegative atom. So we are going to go through sulfate, which is my favorite example to exemplify all of these things. Even though we've kind of talked about them individually, we're going to put it all together with sulfate. We didn't do BH3. We can come back to it. It's not a big deal. I don't want to lose my rhythm. Okay, everybody do whatever they want as far as how to draw this, but go ahead and draw a structure for sulfate. You very well might get different ones. I don't know. I can kind of assume which one you're going to get. Don't forget that you need to add 2 electrons to the structure, though. And because there are a bunch of versions, I'm going to start drawing them now. Oops. Oh my gosh, I love this other way of approaching Lewis structures. I'm realizing that I think you guys are gonna be like, why would I draw it any different way? It just incorporates all of the stuff way better. Oops, so I'm missing one over there. All right, like I think I mentioned this before, but this is the first time that I've embraced teaching Lewis structures this way, and I cannot believe how good it is. Because when you guys look at this, I'm almost sure, now that we've put all the thing of overfilling and all of that together, I'm almost sure that you guys would approach this as needing to have double bonds on one of these, and single bonds, or sorry, on two of these, and single bonds on two of these. Is that where most people went? Because I think the normal high school chemistry approach would be to actually put single bonds on all of them because you're scared of overfilling. Yeah.
So we're only adding 2 electrons total. Not
Yes.
to, each oxygen.
Yes, exactly. The whole structure has 2 electrons. It's like it bonded with calcium and it stole the 2 electrons from the calcium. But the whole structure gets those 2. So I drew them in red. You have to put them somewhere to start. It's always best to put them on the more electronegative atom if it's negative. I will say usually if it's positive, you take them away from the least electronegative atom, but that didn't work out so well in a couple of the examples I did earlier. Well, at least in my other classes. Most of the time it's going to be giving them though, and you give them to the more electronegative atom. So I gave them to the oxygen to start. So let me back up and zoom in on this diagram. Okay, so to make sure we're all on the same page, these were my regular oxygens, sulfurs, and then these 2 oxygens I added an electron to because it was charged, because it was sulfate 2-. When I look at those oxygens that have the electron added on, they look like they only want to form 1 bond. And really, they can only form 1 bond unless I moved the electrons around because oxygen cannot overfill. When I look at the other oxygens, they look like they want to form 2 bonds. And as long as you can get over the fact that sulfur overfills, you should just go with that. Single bond to these ones because they only have the 1 unpaired electron. And then, I don't like how I did that. There we go. And then double bonds to the ones that have 2 electrons that are unpaired. This is what sulfate actually looks like. In theory, and now that I'm looking at it, I'm like, well, no wonder. I don't think you guys would ever think to do this. But when people are very uncomfortable with the idea of overfilling, what they often do is they move an electron from the sulfur to the oxygen. So get rid of those guys. They put them on the oxygen, and then they put single bonds to everything. Because then they're like, okay, everyone has 8 and only 8. So what I want to do, let's pretend that I gave you these 2 structures. Sheesh, can't erase and not, I need to make my eraser smaller apparently. Yep. Okay, so the green ones are the ones that I moved over from the sulfur. So what I want you to do is I want you to put the formal charges on these 2 structures. The one that we did first and the one that I just did. Ignore what I'm doing over here. Okay, I'm gonna put these in red. Go ahead and verify that you got the same thing. Yeah. Yeah. So valence electrons in the free atom minus valence electrons in the molecule. And when I say valence electrons in the molecule, I mean split up the bonds and give 1 to one atom and 1 to the other. Okay, little note, with formal charges, if you did them right, in a neutral molecule like CO2, all of the formal charges should add up to 0. In an ion, all of the formal charges should add up to whatever the charge is, so -2 in this case. So on this structure, I've got -1 on all the oxygens and Over here, zeros on 3 of them, -1 on the oxygens, so they add up to -2. So this is an instance where I can't get everything down to 0. It's just not possible, okay? That's okay. I want them to be as close to 0 as possible. So this structure is way better because I'm getting them a lot closer to 0, obviously, than that one. In order to draw that, I had to move electrons away from the atom that they came in with. That's never really a good thing. It's never really particularly accurate. So back to those 3 rules. Formal charge of 0 is best. If you can't do that, get them as close to 0 as possible. And then finally, put the negative on the more electronegative atom. Okay? So the -1s are on the oxygen, not on the sulfur. Sulfur is less electronegative. We want those negatives on the oxygen. Okay? All right, there's this little bit about bond energies, bond length that we didn't talk about, so that might be one question that you can't do on the homework. We'll talk about that on Monday morning. Yes?
So can you scroll back up to
Yes. The sulfate one?
Yeah. So sulfur's expected behavior is to make 2 bonds.
Yes. Yes.
So like, 'cause I did this first one.
Yeah.
So because it made 4, that's when I should check the chart again.
Yeah, and in fact, I think you approach it from draw the 6 dots around it, and instead of thinking it has to form 2 bonds, think, because in this one, oxygen also wanted to form 2 bonds, now you're at equal of 1. So like, you're offsetting both of them, one way to think of it. Over here, this one's close to what it's supposed to be, this one's close to what it's supposed to be. The sulfur is way off, but sulfur is allowed to overfill. I think the key point for me that I'm seeing that's maybe easier than even having formal charges at the beginning is by going by the fact of if I draw the valence electrons on here, do I have to move any of those to get my structure to work? Like if I have to move these over, that's probably not a good thing.
So you want to like what's the priority to satisfy what it would normally do first?
No. As long as you're following these firm rules about overfilling and underfilling, where did I put those? Those. As long as these are taken care of, sulfur can overfill if it wants. These guys will always underfill. Those ones will always maintain the oxide. As long as you're following those, then go with formal charge.
Okay.
Like, don't worry that sulfur is overfilling, right? Because that's just fine. No issue. Yeah. Yes.
I just got one question. It was at the very beginning, just to know what
Right. So what could you have done?
Hey, that special ed take home
Without
test
that.
is today, right?
Like,
You're in the special
electrical.
ed class after this, right? The take home test is today, right?
So
Okay.
if I've had carbon and oxygen, and I started bonding them,
this morning.
what else would I have done?
I
other
can't keep
than-
track of that class, there's so much.
Right? Like I can't leave it like this.
Okay, so
And the only reason you actually know this,
everything all made sense. But then there's
like that's what
random
this
little signs that
is.
she's put in.
The only reason you know
I
that
don't
that's
know what
not
these
okay
are.
is
Yeah.
because I said carbon, oxygen, nitrogen, and
The
fluorine
nurse IUP
always have
thing, I was like,
contact.
I didn't
They're
know
never
I
gonna
needed to do that
underfill, they're
today.
never gonna.
Right, like I can't tell if it's like in person or like take home.
Yeah.
Like I just did the Eric's IEP thing an hour ago.
Is that a
I don't know if I was
thing
supposed
do?
to.
Oh.
Yeah, I'm gonna do it after this class.
And there was like the 3, whatever, there was apparently
They
good
do.
Monday.
And then you were like, yeah. I saw that, I was like, but we didn't even go over IEPs
Well, maybe
until
that's just because you don't see
yesterday.
Right.
fluorine in biological
So,
systems a whole lot.
I don't
Maybe they
know. It
just
just doesn't
used the
make sense.
acronym if that was the case. So
And I'm
those
like,
guys are underfilling,
That
right?
and then
Carbon's
EdSci
never,
and
ever, ever.
inclusion, and they're all like the same
So to
thing at the
answer
same
your question,
time.
how do I
So
know
I'm
when to
like,
transfer
okay,
electrons?
three of my classes are
Because
over
carbone's never
IEPs.
gonna
What am I
underfill.
doing with each of them?
Did you write down
I feel
these
crazy.
3 things? Oh, okay, good. Good.
I need to write it, so I was like, I think that's what she said.
Row 3 and the rows. Can overfill. And can. Won't necessarily always, but like we just saw with the sulfur, it worked out best to do that.
Okay.
So this is the one that would have made you know that you had to move an electron. Because this is like the priority. If one of these is not, you can never break this stuff. Beyond that, do whatever you want, not have to move electrons around. And that will keep their formal charge the best that it can be.
Will this one always be under? These ones will
Yes.
always?
You will never see an example of that, yeah.
Okay. You're not gonna put that on the test. You're not gonna do it under fill.
No, I'm gonna do an underfill, but I'm saying you'll always see them underfilled. Like this one will always have 2, that one will always have 3, that one will always have 3. You're never gonna see anything where they, it's in, if you look at the columns, this is in the second column, it's in the third, that's in the third. It's how many valence electrons they have.
Okay.
So they just pair up their valence electrons as a bond. Yeah, so these will always, so if there's an example of a test, it will always be 2, 3, and 3. These ones could be 8 electrons, but they could also be more. And these ones will only ever be 8, never more than these.
Okay. Sounds good.
Okay.
You remember I'm not gonna be here next week, right?
Yes, I didn't remember it was next week, but seriously, like, email me that day. No, I'm not kidding. Oh gosh, did I record this class? I said I was going to, and
I saw it on the top.
didn't I push the button? Oh.
I'll email you in my next class, okay?
Okay, yes, thank you. And I'll leave it in my inbox so that I see it on. Yeah, see ya.